The hydrogen molecule. Now, hydrogen molecule is made of two hydrogens, so it shouldn't be that complicated. But I think you're going to find out that it is pretty complicated. And bear in mind, this is the simplest molecule. When we get to nitrogenase, some of those molecules are going to have 50 or 100 orbitals. This only has how many orbitals? Just a quick look at this, we see that there's a electron 1 could go around A, electron 1 could go around B. Now A and B, those are the protons involved. Or electron 2 can do the same thing. So it looks like, oh, maybe there's 4 orbitals. But what about mixtures? There could be mixtures of these orbitals. You could have R going around both of these or something. I don't know. This gets kind of confusing, but at least 4 orbitals instead of 2. And then we've got these pesky repulsion terms that don't occur when you have hydrogen. There's nothing repelling it. Here we've got the protons repelling each other, and then, of course, the 2 electrons repelling each other. One thing we can observe about all this, if we look at those items that are constants, now if you're going to measure this in electron volts, then you'd leave all this garbage in there. And then that'll give you the result in electron volts. If we want to make it simpler and measure it in a unit called Hartrees, then we say that the constant h bar me and e squared over 4 pi e sub 0, just set those equal to 1. Now the mass of the proton, it can't be 1, because if the mass of the electron is 1, then the mass of the proton is 1836 more than the mass of the electron. So let's take these values and plug them in here and see if we can clean this thing up. Here we go. The h bar squared just becomes 1 minus 1/2 1 minus 1 over 3672, which is twice the 1836. And then these look nice. Now, just for a reminder, these are the kinetic energy terms of the 2 electrons that are moving around in space. These are the proton kinetic energies that are moving through space. And let's see, these are the potential energy terms. So you got attractive potential energy and repulsion potential energy. Now, if we were to look at the wave function, that would mean it would depend upon R1, R2, okay, those we expect, but also the location of the A proton and the location of the B proton. Because if they repel each other, then those things can move too, if we all put this in one coordinate system. Well, each one of these is in its own 3-dimensional space. So then in just this lowly little hydrogen thing, we're dealing with 12 dimensions. Just consider what would happen if we had a larger molecule. The dimensions are just going to explode, and trying to calculate all that stuff is going to be a big mess. So what we'll do in the next video is show you an approximation that will help clean all this stuff up.